Hello everyone, today we will be doing the full physics revision where we will complete all physics chapters of class 10th CBSE, which will be coming for your boards, which will be light, reflection and refraction, human eye and the colorful world, electricity and magnetic effects of electric current. We'll be completing all the 4 chapters in this video, and we'll be doing this in the way like first we'll do all the important concepts. We will also see what is the different CBSE weightage for each chapter, and we will see how you can study for this chapter. So subscribe to the channel and like this video and watch it until the end so that you grab all the concepts and you can be thorough for your exam. So let's start with light, reflection and refraction. So this chapter has a weightage of 10 to 13 marks, which is a very high weightage chapter, and most questions that come are usually numericals or ray diagrams and some definitions and laws that can be asked. So the best way is to practice all the sums, prepare a formula sheet or notes, etc. Same way, you can always join the WhatsApp channel where we share the notes of all chapters along with some sample papers and practice questions. You can comment below for the link to the WhatsApp channel. Now coming to the first topic in light, reflection and refraction. What is reflection? Like, what happens when you see yourself in the mirror? So what is happening here is that the light falls on the polished surface and it bounces back instead of passing through. This phenomenon is called reflection. That is, it hits the reflective surface and it comes back, which is a reflection. And there are certain laws of reflection that we follow, which is the angle of incidence is always equal to the angle of reflection. At what angle the incident ray is to the normal, the same angle the reflected ray will be, and the incident ray, the reflected ray and the normal to the mirror all lie in the same plane. That is, all of them are on the same plane. There is no 3-4 dimensions here. It is all happening in one dimension is what that means. So now moving on to image formation by a plane mirror. So when you look at yourself in the mirror, what is happening if this is your object here and the image is formed behind the mirror? So the first thing that we see is the image is virtual and erect. It is upright. You don't see yourself inverted. It is the same size as that of the object. Whatever the object size is, same size as that of the object. The object and the image both are equidistant from the mirror. It is equidistant. The third thing is laterally inverted. That is, this is my left hand, but it appears to be right hand in the mirror. So that is called lateral inversion. So now coming to spherical mirrors, which are what we are going to learn in this reflection chapter. So starting first with a convex mirror. So in a convex mirror, you have a curved polished surface. The outer side is reflective. The inner side is darkened or black. It's a convex mirror. And the other mirror is a concave mirror where the inner side is reflective and the outer side is shaded back. So this is a concave and convex mirror. So now there are some parts of these mirrors that we need to know. So every mirror is actually part of a circle. If you see, if I complete it, it's a circle. So there is a center of this circle, correct? I can call that center of the circle as the center of curvature of the circle, correct? And the distance from this point where this is touching, okay, to the center is called the radius of curvature. This distance is called the radius of curvature for both the mirrors. And at half of this distance, you have a point called focus point at half of the radius of curvature. That is, F is equal to 2 times F will be equal to R. So this distance is called the half of the radius of curvature is called the focal point, and the distance from the mirror to the focal point is called the focal length, right? Represented by small f. Now, why is it called the focal point, or what is it half is? All the incident rays that fall on the mirror, if I place rays on the mirror like this, for a concave mirror, they appear to converge at that point. So all the rays will converge at that point. And for a convex mirror, they get diverged but appear to merge at the focal point. So if we see in a better diagram, So for a convex mirror, all the incident rays that we see appear to merge at a point which is called the focus point, and it is half of the center of curvature. Same way for a concave mirror, all the reflected rays will merge at a point which is called the focal point, and the distance from this pole to the focal point is called the focus of the mirror, and twice the focus is equal to this distance from pole to C or center of curvature, which is called the radius of curvature of that mirror. So based on this, there are multiple images and types of images that are formed in the mirror. Coming to what are the different kinds of image formation by the mirror. So we'll go with the image formation of convex mirror first, where in the first case, I place my object at infinity. And if the object is somewhere at infinity, then my image will be formed at focus. Okay. And it will be highly diminished. As you can see, it's very small. There is no image. It is point sized and it will be virtual and erect. When if I move the object anywhere closer between infinity to pole, if I keep it anywhere, then the image is formed between pole and focus behind the mirror. It is virtual and erect and it is diminished. See, you can see the size has reduced drastically. It is diminished then compared to what we saw earlier. Now coming to image formation by concave mirror. Here there are 6 cases, so we will look one by one. So first, if my object is at infinity, the image will again be formed at focus, but since it is formed this side of the mirror, it is real and inverted and it is highly diminished or point sized. Now if I move the object to beyond C, that is I bring it closer to the mirror, then the image will be formed between C and F. It is diminished and it is real and inverted. You can see the image going below. Now next time, the image further closer and bring it at C. I bring the object further closer to at C, then my image will also be at C and the size is same. It is exactly the same size as that of the object and the nature of the image is real and inverted. This case is asked mostly in numericals in terms of saying that the object was placed at a position where the image was same size or the magnification of the image was -1. All these are indications that the object was placed at C and the image is placed will be also at C. Coming to further closer the object moving between C and F, then the image is formed beyond C, it is enlarged and it is real and inverted. The next case, I'll move the image further closer to between on the focus point, then the image will be formed at infinity. It will be highly enlarged, real and inverted. And if I put it between F and P, the object, the image will be formed behind the mirror. It will be virtual and erect and it will be enlarged, as you can see here. These are the 6 cases of concave mirror image formation which you are supposed to remember. You can always see that as you bring the object closer, the image goes farther away and it starts getting bigger and bigger. So coming to the uses of mirrors in concave mirror and convex mirror, what happens is concave mirrors are used in torchlights and searchlights and dental mirrors which the doctor sees your teeth with to get high enlarged images, solar furnaces to focus the sunlight on a particular point. So all these places concave mirrors are used because they generate enlarged images. Convex mirrors are used in rear view mirrors of cars, like you can see here. So the image is generally virtual and direct, and because it is like convex, like the outer surface, it gives a wider view to the driver. And even though the image is diminished, you get to see more objects at once, which helps the driver in driving easily. So these are the uses of these mirrors. Coming to the sign convention for mirrors. So here we'll learn the different sign conventions of mirrors. So here what you do is you understand that the pole of the mirror is considered the 0 of your number line, which is having 1, 2, 3, etc. So in that sense, if you see, anything that is on this side of the number line is positive, same like your number line. Anything that is this side is positive, anything above is positive, and anything on your left is always negative. This is where your negative numbers are, and anything which is below is negative. So in that context, the pole of the mirror is always considered as 0 and the principal axis is taken as the x-axis. So all distances measured to the left of the pole are considered to be negative Any distance measured to the right is considered positive. Above is positive, below is negative. So now if we see for a concave mirror, what happens is always object is placed on this side of the mirror. So always the object distance will be negative. For any mirror, the object distance will always be negative because you are placing it on this side. And because the concave mirror's focus is on this side, it will always be negative. The object that you place will always be positive, and if it's a real and inverted image, it will be negative. So in the case of a convex mirror, what happens is the object height will be positive, the object distance will be negative because it's on this side, but the focal length of the convex mirror will always be positive. And the image, if it will be virtual and erect, so it will be positive. Remembering this helps you in numericals because no one explicitly says that the focal length is minus 20. They will say for a concave mirror the focal length is 20. So you have to assume that the focal length is minus 20, or the object is placed at 10 centimeters. So you have to take minus 10 centimeters to solve your numerical. We'll be doing a video on all the numericals for all the physics chapters that will be coming up next week. So keep a watch on that. Now coming to mirror formula. So that is what is called the focal length of the mirror. So this is what is there for. So similarly, even for concave mirror, you have to take these values as per sign convention to solve your numericals. Coming to magnification, which shows how much the object has diminished or enlarged, what we do here is we calculate the magnification as height of the image by height of the object, which is also given by minus v by u. So here, and the height of the image and height of the object is taken. So minus v by u, where v is the image distance and u is the object distance. This is also a formula for magnification. So you can get numericals which links both the formulas along with using the formula of r is equal to 2f, and also some basic understanding on where the image would be if the object is here. So all of this combined analytically, they can ask questions. We'll be doing a video on all the important numericals of physics, and you can gather enough information from there. Coming to refraction, whereas what is refraction is, it's the bending of light. So when light travels from one medium to another medium, light bends. And this bending of light from one medium to another is called refraction. So this is why when you put a pencil in a glass of water, it is moving from air to water. So the medium has changed. So there is a slight bend in the pencil when you see it. So this is an example of refraction. Now, the laws of refraction there are two laws of refraction. The first one is that the incident ray and the refracted ray and the normal are all of any two media are all lying on the same plane. That is, again, there is no multi-dimension here. Now, the second law of refraction is also called the Snell's law, where the ratio of the sine of the angle of incidence and the sine of the angle of refraction is a constant. And this happens only for a given light of given color and a given pair of media. Always remember, when you're writing any laws in physics, you have to write the conditions under which the law is true, because that law holds true only in that situation. If you change the color of light or the given pair of media, the law won't hold true. So the marks when you lose in these questions is purely because you are missing out on writing these conditions, right? So if I write it in a numerical form, sin I by sin r is a constant. Now always, whenever there's a question that states state the law, always write the word format of the law, not the formula. This is the formula or the mathematical interpretation of this. Writing it in words along with its reasons or conditions is what fetches you full marks in those theory questions. Coming to refraction through a glass slab. So if I take a glass slab, where previously what we did, we closed it. We ensured that the light stays in this medium. It never came out of it. The next part was opaque. So now we're taking a glass slab and seeing how does it change if it goes from medium 1 to 2, then back from 2 to 1. So here we observe that light will bend towards the normal when it travels from rarer medium to denser medium, and light will bend away from the normal when it travels from denser medium to rarer medium. So this density and rarity of the material is given through refractive index that we will see. So let us see refractive index, which explains that light bending and why it bends or how much it will bend in a particular medium. So what is happening? Why is light bending per se? Is because it changes its speed as it moves into a different medium. So if in one medium it has one speed, the speed of light changes in the other medium. As we know, there are different speeds of light. So the amount of change in the speed in the direction of light is measured in terms of refractive index. It's a dimensionless quantity which is compares the ratio of the speed of light in one medium compared to the speed of light in other medium. And if you compare it against the speed of light in vacuum, which is 3 into 10 to the power 8 meters per second, it is called absolute refractive index. So if I want to find out the refractive index of medium 2 with respect to medium 1, it is speed of light in medium 1 divided by the speed of light in medium 2. So if it is 2 1, the 1 and 2 will be on the top. So if I want the absolute refractive index of medium 2, which is with respect to medium 1 is vacuum, it will be 3 into 10 to the powers of 8 divided by the speed of light in the second medium. That is how you find the refractive index of an medium. Sometimes there are questions on refractive index. Understand this ratio, do not get confused, and keep it very easy in memory and stick to one formula. You will be able to solve the numericals of this question. Coming to spherical lenses, where this refraction is used to form images. So again, if you merge two convex mirrors, you form a convex lens, and if two concave mirrors are merged, you get a concave lens. Now these two lenses, they have there will be you can have one circle here, one circle here, so they will have center of curvatures on both the ends depending on which circle they are, and the center at which the two lenses join is called the optic center. Again, this is the principal axis, so this happens for both the mirrors. Again, this is also part of a circle here, so the center of this circle, so that is generally called the 2f1 2f2 points of the lenses. So it is 2f1 and 2f2 points, and again where all the refracted rays will meet is called the focal length of the lens. So with this, the C1 and C2 points are called the 2f1 and 2f2 points of the lenses, and where all the rays would meet is the f2 point in case of convex lens, and it will be the f1 point in case of concave lens. So this is a converging lens and this is a diverging lens. As it diverges its refracted rays, and the distance from the optic center to the focus is again called the focal length. 2f1 2f2 point is double the focal length. So again, we'll be starting from infinity, where the object is placed at infinity, and we will see where the image is formed. So when you place the object at infinity, the image is again formed at focus. It is highly diminished, real and inverted. Bringing it further closer to beyond the 2f1 or c1 point, the image will be formed on the other side of the lens, and it will be between f2 and 2f2 point, and it will be diminished, real and inverted. Similarly, again in the case of, if I put it at 2f1 point, it will be at 2f2 point. It will be same size, same like at C, and will be real and inverted. Similarly, 2f1 and between f1 point, if my object is placed, it will be beyond C. The image will come beyond C. It will be enlarged, real and inverted. Coming to the last two cases, where if the object is placed at focus or f1 point, the image will be at infinity. Similarly, if the object is placed between the optic center and f1 point, if the object is placed, then the image will be on the same side as that of the object, and it will be enlarged, and it will be virtual and erect. This is how the convex lens forms images. And in the case of concave lens, there will be two cases. First, if the object is placed at infinity, the image will be formed at focus point, which is highly diminished, and it is point sized. It will be virtual and direct. If the object is placed anywhere between infinity and the optic center, the image will be formed between the focus and the optic center. It will be diminished and virtual and erect. This is how a concave lens will form mirrors. Now, why the other two ends exist is sometimes you can place the mirror like this. So then this will become the f1, this will become the f2. So that's why they are interchangeable. You can place the object at any side for a lens. So now coming to the sign convention of lenses, which is very similar to that of the mirrors, where the optic center is 0, the principal axis is the x-axis. So everything this side is positive, everything this side is negative, below is negative, above is positive. So similarly, for a concave lens, the focal length will be negative and the object will be always the object will be positive, but the distance of the object will be negative and the image will be negative. And coming to the convex lens, the focal length will be positive for a convex lens and the image will be always positive. The image, if it is virtual, it will be positive because the distance is present on this side of the lens. Now coming to the lens formula that we will revise. So again, this lens formula is similar to your mirror formula. It's just that it's 1 by v minus 1 by u by 1 by f. Again, u here means the object distance, v means the image distance, and f is the focus length. So the magnification formula is given as m is equal to image height by object height, where the image distance divided by the object distance. There is no minus here, so you can remember it like in the lens formula there's a minus, so the magnification doesn't have a formula. And similarly in the case of mirror formula, the minus lies in the magnification, not in the mirror formula. So again here h is the object height and h dash is the image height, where v and u are image distance and object distance respectively. There's an additional formula here for power of a lens, where 1 by f is called the power of the lens. The power of the lens is given by 1 by f. So this completes your light reflection and refraction chapter. This is not a theory chapter to understand, so we went a little fast in just revising all the formulas. We will be doing a video on all numericals that can help you master this chapter much better. Coming to the next chapter that we have, which is human eye and the colorful world, where we'll be learning the different phenomenon and about our human eye and how it functions with respect to reflection or refraction. So this chapter has a weightage of 3 to 5 marks, and mostly the defects of the eyes and explanation of natural phenomenon is what it's asked. So always, because it has a little theory involved, so making notes, drawing diagrams is most important in this chapter. Again, you can join the WhatsApp channel, comment below for the link, and you will be able to get the notes of all these chapters. Coming to the human eye, which is an organ that is present, which enables us to see the world. Let's just see the different parts and its functions, starting with retina, which is this end which is actually responsible for the image formation. So it's a light sensitive screen which is present inside the eye, okay, and it contains light sensitive cells that illuminate and form a real image on the surface. So it has those optic nerve cells which are photoreceptors that we saw in our control coordination chapter, where we see that any light changes, those receptors can grab a signal. So it has those light sensitive cells that illuminate and form a real image on its surface. The image is then interpreted by the optic nerve which is present here. Coming to cornea, which is this outer layer, the white outer layer that you see, this one, this is cornea which is present, and the light enters the eye through this thin membrane of cornea. Maximum refraction occurs here itself in the cornea, and between the cornea and the lens there is an aqueous humor which is like a liquid structure which acts as a lens along with the cornea. Coming to the next part, which is the iris, which is actually what is giving you those lines of color. This iris is a dark muscular assembly behind the cornea, and it controls your pupil size. Pupil is that center round circle that you see, and that determines how much light has to enter in the eye. So what happens with the help of iris, it becomes small and bright light to reduce the amount of light that is coming into your eye, and becomes large in dim light to increase more light coming into your eye. Coming to the next part, which is the crystalline lens, which actually is the lens in your eye which is helping you see. This provides the finer adjustment of focal length. So refraction has already occurred in cornea, so the crystalline lens will help you create that adjust of focal length of finally finding a correct spot where you can see the image clearly. It focuses on objects lying at various distances on retina. And this focusing happens with the help of ciliary muscles which are present on the side. These muscles change the curvature of the lens. So they'll make it bulged or small. So that changing curvature of the lens will help you focus on the object that you want to see. This ciliary muscles contract for looking at nearby objects and relax for looking at distant objects. It helps focus the object for both near and far objects. Okay. So the next thing is the power of accommodation. which is the ability of this eye to focus at nearby and distant object by changing its focal length. So the ability of the eye to focus, so it can keep moving. So how does it change its focus? Is using the ciliary muscle. So the near point is the point where the muscles contract, lens becomes thick to view nearby objects, and the least distance of distinct vision, or the minimum distance at which objects can be seen, like at what distance if I place my hand I can see it clearly, is 25 centimeter for a normal eye. Okay, so this is called the least distance of distinct vision. Coming to far point. Far point is the farthest that you can see. So the muscles, the ciliary muscles relax, become thin to view distant objects. So the farthest point up to which the eye can see clearly is infinity for a normal eye. Now coming to certain defects in vision that can occur. So as you can see, I'm wearing a specs. I cannot see without these specs. So without these specs, my vision will be blurred. I am not blind. It's not blindness. You can see, but you cannot see clearly. Why is that happening? Is because my lens has lost the ability to focus. I am not able to focus clearly on the retina. So what happens in myopia, which is what I have also, is called, you cannot see far away objects. You cannot see objects which are far away. So that is why it is called nearsightedness. And the image is generally formed in front of the retina. So my image is formed in front of the retina and I'm unable to see the object. So I correct it with the help of a concave lens. So as you see, my specs, if you can see clearly or not, it will be thin in the middle and bulged on the sides, which shows that it is a concave lens which helps correct this vision. So it ensures that the image is converged and diverged correctly, such that the image is formed on the retina. So what happens here is a person cannot see far away objects, and it is called nearsightedness. The image, because I can see near, so nearsighted, I have nearsight is there, but I cannot see far away objects. That is why it's called nearsightedness. The image is formed in front of the retina, and this is caused due to excessive curvature of eye lens or elongation of the eyeball. You correct this using a concave diverging lens of suitable focal length to be able to focus it back onto the retina. This is called myopia. The next one we have is hypermetropia, where a person cannot see nearby objects. You cannot see anything which is near. So because here the image is formed behind the retina, and this is corrected using a convex lens and it is put back onto the retina. This happens because there is a large focal length of the eye, shortening of eyeball. Like in myopia it was elongation of eyeball, here the eyeball has shortened. So you correct this using a convex lens which converges the image back onto the retina. Now coming to presbyopia. Here the person who has myopia cannot see near objects due to age. So as if I grow old and I cannot see nearby objects, my myopia becomes presbyopia because I already have myopia. So what happens is the far away objects, the image is formed in front of the retina. Nearby objects, the image is formed behind the retina. So it is corrected using bifocal lens. The lens on the top is a concave lens to see far away objects, and here you have a convex lens to see nearby objects. So this is how you correct presbyopia, and it is usually caused due to weakening of ciliary muscles and flexibility decrease in the crystalline lens over the years due to age. Okay, this is how you correct presbyopia. There's another disorder that can occur, that is cataract. This also occurs at old age, where the crystalline lens you see here becomes cloudy. So there's a milky layer inside the lens, and this is usually corrected through surgery where the lens is changed. Okay, so this is called cataract. Now we will move towards refraction through prism. We have seen how refraction occurs through a glass slab in the last chapter. So now if I make the glass slab ends as a triangle, how does the refraction occur is what we are going to see. So if you see here, if my incident ray is put on the surface of the prism, I will first bend my light in one direction. I will move from rarer medium to denser medium. So light will move towards the normal and it will pass through. And once it passes through, in case of a glass slab, we saw that it will emerge out and it will be equal, the incident ray angle and the emergent ray angle will be equal, but usually that might not occur in the case of prism, and there is an angle of deviation here which is telling you the difference between the refraction in prism. So the again it bends outward, and this is the angle of emergence, and this angle of incidence normal and this emergent normal gives rise to the angle of deviation, and this the angle between the angle of incident ray and the emergent ray is called the angle of deviation. This occurs in the case of prism. So now because of this, there is also the light is bending, but it's bending differently. It's bending twice. There is some phenomenon called as dispersion of light. So when a light passes through prism, it disperses or it shows its spectrum. So a white light has components of all the colors of rainbow, which is VIBGYOR, which is violet, indigo, blue, green, yellow, orange and red. And this comes out through the prism. So it is the splitting of white light into its color components, which is called the dispersion of light. And this occurs because each color of light has a different wavelength and it bends differently as it passes through the prism. So the red light bends the least and the violet light bends the most, and this phenomenon of dispersion explains the phenomenon of rainbows. So how is rainbow formed? Rainbows are usually formed when there is sunlight while the rain is occurring and the sun is on the opposite direction of that of the viewer. So in that case, so the light from the sun comes onto the raindrop, and it raindrop becomes your prism here, and it first gets dispersed and refracted inside. Once it's refracted, it undergoes total internal reflection inside the raindrop, and it gets refracted out as a rainbow. That is how you can see a rainbow formation that occurs. Okay, and the dispersion of light explains the rainbow formation. Coming to atmospheric refraction, so as we know, atmosphere is made of multiple layers, and the air in the atmosphere is not of same density throughout. There is different density of atmospheric air in terms of as we go up. So when light passes through the atmosphere, the light passes through, gets refracted multiple times because it bends towards the normal, away from the normal, towards the normal, away from the normal, as it gets changing its medium. So the light passing through gets refracted multiple times. So what happens because of this is, objects that you see at a particular position is not their actual position. It could be because of refraction, and the actual position could be somewhere. This theory explains multiple phenomena such as twinkling of stars and advanced sunrise and sunset, which we will see now. So the twinkling of stars occurs because now this is the real position of the star. It undergoes so much refraction as it passes through the atmosphere. At one point it appears at one position, at another point it appears at other position, but the star is at the same place. It is just the refraction which makes you feel that it is switching its position. That is how the stars appear to be twinkling, and this position keeps fluctuating, which causes that twinkling effect. But why don't planets twinkle? Because planets are much closer to Earth, and there are a collection of large sources of light. So there's not just one source of light. So what happens? Multiple sources of light come, and the net refraction becomes zero, and it nullifies the twinkling effect. So you see planet only at one place. So because it's much closer, the amount of refraction it undergoes is also much less. So why do we see advanced sunrise and sunset also is the same reason, because if the real sun is here and if it is crossing horizon at this point, we see that it crosses it here because at 2 minutes little early we see them to cross horizon, because if this is the real sun's position, there is internal refraction here that makes us believe that the apparent position of the sun is here. Coming to scattering of light, which is the changing in the direction of light on striking an object of dust particle or water drop. So the water changes its direction as it strikes any object. Because of this, we can see a Tyndall effect which happens in the forest, where the scattering of light occurs due to colloidal particles, and the scattered light and the color of scattering depends on the size of the particle, and the sunlight passes through this full canopy of dense forests is called Tyndall effect that occurs. Now, the blue color of the sky that we see is also because of this scattering of light, where the sky is blue because blue has a shorter wavelength and it is scattered most, because of which we see the blue color of the sky predominantly, and red is scattered least, so we cannot see it much in the sky. So that is the reason our sky is mostly blue in color when we see it. So this explains all the phenomenon that we natural phenomenon that we have using dispersion of light, which shows us rainbows, a refraction of atmospheric refraction, which shows us twinkling of stars, advanced sunset and sunrise, scattering of light, which shows Tyndall effect and blue color of the sky. All these are important phenomena. Understanding why and what causes it is important for your theory questions. Coming to the next chapter that we have, which is electricity. Here again, this is a formula intensive chapter where there will be numericals, so it is worth of 8 to 10 marks, and there are different definitions and laws that you need to remember for this chapter. Again, wherever there are laws and definitions, you need to remember and write the exact law. So you can make formula sheets and notes. Again, comment below for link to the WhatsApp channel where we share all these notes of physics. So let us start first with electric current, which is the first definition of electricity that we need to do. So electric current is basically how much electrons are flowing through a conductor of any cross section in a given amount of time. So the rate of flow of electrons or charge per unit time is called electric current. So it is given by I, which is electric current is given by I, which is equal to Q by T. Q is nothing but the amount of charge per unit time is called the electric current. Now, the further definitions of this, where the unit of which with which we measure this is called ampere, represented by an A, and it is measured using the device ammeter. And the other units that we use, 1 ampere of current is very huge current. So the general use of the general currents that we usually have are 1 milliampere current, which is 10 to the power minus 3 amperes, and 1 microampere, which is 10 to the power of minus 6 ampere. The current that flows through our body through electric signals is in the tune of nanoampere, which is like 10 to the power minus 9 amperes, and 1 ampere of current. So in this chapter there will be definitions of 1 ampere, 1 volt, 1 ohm, 1 watt. These definitions are very important for your board exam, where you define what is 1 ampere of current. So the 1 ampere of current is, you replace everything by 1 in the definition. Flow of 1 coulomb of charge per 1 second is the 1 ampere current. That is how you define 1 ampere of current. So now next, coming to voltage or potential difference, what it essentially means is, now this charge is there here, I take it and move it to another place. Now little mechanics is involved here, where you understand that what is work done. We studied this in 9th class. Work done is nothing but force with displacement, right? Force into displacement or distance. Force into distance is nothing but the work done. So you apply a force and move an object from one place to another, you are doing some work. So the work done per unit charge, so per charge how much work is done is given by the potential difference. So the work done to move this unit charge from one point to another is called potential difference. Because if let's say all charges are here, I move from different places, I take different charges. For example, here there is one charge, here there is one charge. I take each charge and start moving it to one location. I have a collection of charge here. So this collection of charge creates a potential difference between 2 points. That is why it is called potential difference. And this is given by V, which is work done per charge. You'll learn more about this electric static charges, etc. in your class 12th. It's a very interesting chapter, and you'll learn clearly what moving of a charge and all of that mean. So coming to the different SI unit and measurement devices of this, SI unit of potential difference is volt, which is given by V, and the measurement device is a voltmeter. Now the flow of current is basically taken from positive terminal of the cell to the negative terminal of the cell. Cell is where I have collected all my charges and kept. It's like a battery. Battery is multiple cells placed together is called a battery. So I have collection of cells here, so that will help If I put this collection of cells in a circuit, the electrons will start flowing. So this flow or the direction of flow is taken from positive terminal to the negative terminal. Again, we need to define what is 1 volt. 1 volt is 1 joule of work done to move 1 coulomb of charge from one point to another. You replace everything with 1. So coming to the next point is resistance. A potential difference creates that force for that charge to move. No charge will move on its own. You need to create force. How do you create that force? You create it with the help of potential difference. I have so many charges here, so start flowing in one direction. So the conductor causes that current or rate of flow of electrons. Resistance will stop this flow of electrons or resist the amount of electrons that will flow in the circuit. So it is the basic ability of the metallic wire. It's essentially a wire wound in different ways to form different current levels of resistance. So it's the ability of the wire to restrict the flow of electrons, and it is used in circuits to reduce the current flow. Coming to Ohm's law. Now Ohm's law is the law which tries to find a relation between all the three that we have studied: current, voltage and resistance. We are trying to draw a relation between all the three. So for this we do an experiment where we take one resistor. Okay, this is a resistor which is placed in a circuit. Okay, and in this circuit we have connected it to different cells here, and there's an ammeter. So as we keep increasing the voltage, we will measure the voltage across this resistor and the current that is flowing in the circuit. Okay, so once I close the key, we will be measuring the voltmeter and ammeter readings as we increase the voltage in the cells. So when you do this experiment, you will see that if I use one cell and my voltmeter reading was 5 ampere, the ammeter reading is 2 ampere. So I do what is V by I. V by I is 2.5. Similarly, if I use 2 cells, I am getting 10 volt and 4 ampere. 3 cells 15 volt 6 ampere, and 4 cells I got 20 volt and 8 ampere. This is the voltage that I got across this resistor and the current that is flowing in the circuit. In all the cases, the ratio of V by I remains a constant, which is what we understand from Ohm's law. That is, if you plot a graph between V and I, you have a graph which is passing through the origin and it is a straight line. So the VI graph is a straight line and V by I ratio is always a constant. So V is proportional to I. This is what it means. V is proportional to I. So as you increase V, I also increases. So with this, we remove the proportionality constant and replace it by resistance R, which is the value of the resistance, which shows that V is equal to IR. This is nothing but your Ohm's law. Okay, this is not the law, this is the mathematical interpretation of this. We will write the law in a while. So resistance is a constant and at a given temperature for a given metallic wire. So it's usually a constant for a given metallic wire. So the Ohm's law states that the potential difference across the ends of a metallic wire in an electric circuit is directly proportional to the current flowing through it, provided the temperature remains same. Writing this provided temperature remains same is essentially important for this law. So the potential difference across this wire is potential to the current that flows through it, directly proportional to the current that flows through it, provided the temperature remains same. In that given condition of temperature, this potential difference and the current are always directly proportional for a given metallic wire. That is Ohm's law. With this, we can understand that resistance is the ability of the metallic wire to restrict flow of electrons, and R is given by V by I, which is the slope of the graph. And the SI unit of this is given by ohm, which has the symbol of omega from the Greek language. And definition of 1 ohm is if a potential difference across two ends of a conductor is 1 volt and the current through it is 1 ampere, then the resistance is 1 ohm and the resistance through the conductor is 1 ohm. This is how we interpret resistance. Now coming to the factors that affect resistance, like what affects resistance is, so if I take this resistance, I can see that if the length of the wire is increased, then the resistance will also increase, which means that if resistance has to be increased, I can increase the length of the wire. So it is directly proportional to the resistance. The next thing I see is if I increase the area of cross section, that is if I make it more wide, more electrons will flow, so resistance will come down. So it is inversely proportional to the resistance that we see. So that is an inversely proportional resistance. So the resistance is inversely proportional to the area of cross section to of that wire. So combining these two, I can write that R is proportional to L by A. L is the length and A is the area of cross section. So removing the proportionality constant, we put rho. Rho is nothing but constant of resistivity for a given temperature. It is a characteristic property of the material to allow the flow of electrons or not. So some conductors etc. have very low resistivity, and insulators like rubber and plastic will have high rhos, which are like highest level of resistivity towards electric current. These are the factors that affect resistance. So the next thing is system of resistance, where you connect multiple resistance in multiple ways and how each system is different, and how we find out what is the combined resistance of that system. So if the resistors are connected end to end, like one after the other, it is called connected in series. And if they are connected one below the other, like both the ends of each resistor are connected to each other, that is called a parallel connection. So in both the cases there is a certain difference. In the case of series connection, as you see, the current will flow in this direction. So the same current will flow in all the resistance, but each of them will have different voltage across each of them. So there is different potential difference across each resistor. But in the case of parallel, different current will flow, because when I connect it like this to a circuit, the current will split at this junction. I will have different currents flowing through, but the potential difference across these ends will always be V. So the current through the resistor remains same in each resistor. There is a different potential difference across each resistor in the case of series. So the potential difference would be sum of all potential differences, V1 plus V2 plus V3. So when I apply Ohm's law to this, I can write V is equal to IR, where IR is given by the current that is flowing through and the value of resistor. So for each V1 you will get, so IR will be equal to IR1 plus IR2 plus IR3. So if I remove the I from this equation, I can write the equivalent resistance in series as R1 plus R2 plus R3. So if I add up all the resistors, I will get the equivalent resistors in the case of series. In the case of parallel, what happens is, the potential difference is same, but the different current will flow across each resistor. So since different current will flow, total current would be I1 plus I2 plus I3. And applying Ohm's law again, V by R will be equal to V by R1 plus V by R2 plus V by R3. So in parallel, it will be 1 by R will be equal to 1 by R1 plus 1 by R2 plus 1 by R3. So that is how you create a difference in each of the resistor. That is the formula for resistors connected in parallel and how you will get the total equivalent resistance. So here let us summarize what we have learned so far. So when connected in series, the current remains same, but it is different in case of parallel. In parallel, it will be different across each resistor. The voltage will be different across each resistor in series, but it remains same in parallel. The effective resistance will be R1 plus R2 plus R3 in series, and 1 by R will be equal to 1 by R1 plus 1 by R2 plus 1 by R3 in parallel. In the circuit, when they are connected in series, the resistance reduces the current flow, but when connected in parallel, it is to ensure that same potential difference is maintained across different resistors that you add together. So let us see how you determine in this circuit what is series, what is parallel. So first let me label them. Let me say this is R1, this is R2, this is R3, this is R4. So always the best trick to use to determine whether series or parallel is to go with the flow of current. If the current is dividing, it is parallel. If the current is not dividing, it is series. So how will the current flow from positive terminal to negative? So it will go and come back like this. So the current starts here, it divides here. So that says that this R1 is in parallel with this big system. So R1 is in parallel with that big entire system that we have. In this system, R2 is going, again the current divides here. So what I can conclude is R3 is in parallel with R4. This parallel system is in series. So this is in series with R2. And this entire system, R1, is in parallel with this entire R3, R2, R3 parallel system. So that is how you draw. This is the easiest way to determine if a system is in series or parallel. Always go with the direction of current. Never ever go with how they are connected. You will go wrong, right? It appears to be parallel, but they could be in series. So always use if the current is dividing, they are parallel. If the current is not dividing, they are in series. Coming to the next one, which is the heating effect of electric current, where in any circuit, when you connect anything which is resistive, the energy in that circuit is dissipated as heat. So the battery, which has all the cells in it, expenses its energy to keep the electrons flowing. So it uses up energy to keep that energy of electrons flowing, and most of this energy is used by electrons to move in the circuit, and some of it is lost as heat in the circuit. So some heat is dissipated in the circuit. So now this, how do we calculate how much heat is dissipated is, let us say the work done to move this charge across this potential difference. Okay, so work done to move this charge flowing across during the time t through the potential difference of V. So if I take this charge and move it from here to here, okay, during this potential difference for a time t, then I'll give the work done as potential difference into Q. We know that potential difference is work done by Q, right? So I will multiply this Q with potential difference to get my work done. So if this is my work done, power is nothing but work done by time. So work done, so which is VQ, will be equal to T, right? Then I will write Q by T as I. Q by T as I. So power is nothing but V into I. So this power into time is called energy. Power into time is energy. In this case, I am going to call it heat, H. So now power will be VI into T. So if I apply Ohm's law to this, I get the formula H is equal to I square R T. So this is one of the formula of heating effect of current, which can be asked in numericals also. And you can substitute and get your answer. It would be straightforward, but ensure you use all the formulas possible, like there could be Ohm's law linkage. So this heating effect of current is used in multiple situations where such as all your toasters, electric kettle, radiators, electric iron, ovens, all these places is where you use this heating effect of the oven. The another use is your electric bulb, where the heat is used to generate light. So you see this, the one which is illuminating here is called the filament, and it is made of a strong metal called tungsten, and this tungsten has a high melting point. So because it has a high melting point, what happens, it absorbs all the heat and it gets so hot that it starts emitting light. So that is how it shows that that is how it emits light through the system. Now coming to electric fuse, which is used to prevent any damage in the circuit. It is usually connected in series. So it is basically a fuse or an alloy which is made of a suitable melting point. So if a current that goes larger than a specific amount comes through the circuit, that fuse will melt and it will break the circuit, which will protect all other appliances that happen. We will learn more about fuse in the next chapter as well. Now coming to electric power. Electric power is again what we have discussed. So if I have a charge Q and I move it across this potential difference so that it completes the circuit, this Q movement from this negative to positive terminal across this potential difference of V. So that work done will be given again by V into Q, and this power is work done by time. So VQ by T, Q by T can be written as I. So power is nothing but V into I. So if I apply Ohm's law, I can write power as I square R or V square by R. So these are the two situations of power. Now power has an SI unit of watt, and there are other units which is like 1 kilowatt hour or 3600 kilojoules, which is nothing but 1000 watts into 3600 seconds. That is total seconds in an hour. So what is 1 watt? 1 watt is the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. So now let us move to the next chapter, or the smallest chapter of physics that we have, which is magnetic effects of electric current. Okay, so where we'll see how electricity can cause magnetism. So this chapter is a small chapter where the weightage is 3 to 5 marks. The most repeated questions are the right hand rule, left hand Fleming's rule, and some definitions and laws that are part of this chapter. In this chapter, you need to prepare a formula sheet and notes for basics, and there is always practice the direction of current in all the different cases that will come. We will learn more in this chapter as we do it. So let us start with understanding. So you can always again comment below for the WhatsApp link where we share all the PDF of the notes and the formula sheets of this chapter. Coming to first concept, which is magnetism. Magnet is an object that exerts a certain magnetic force around it, and this force is called a magnetic field, which has both direction and magnitude. So the field lines usually emerge from the north pole. Okay, so they start from the north pole, and if this is the south pole, so they start from the north pole and go to the south pole. So it's a complete loop. And these, generally it is observed that the like poles repel each other. Like if you bring a south pole and south pole together, they will not touch each other, they will start repelling. And if you bring opposite poles, which is north and south, together, they attract each other. That is, the two magnets start meeting. So coming to magnetic field lines that we have. So like I said, the magnetic field lines have certain properties. That is, one, they start at the north and merge at the south outside the magnet. They do not intersect with each other, and they form a closed loop. Inside the magnet, they go from south to north. And the closer the field lines, stronger is the magnetic field. Now this is generally about how magnets behave. You can take your fridge magnet, that would also behave the same way. Now coming to, can electricity cause magnetism? So what one experiment was conducted where a conductor or a conducting wire was placed and it was connected to a circuit, and then a compass was brought closer, and it was seen that the compass needle showed deflection as in it keeps turning the other side. So that deflection is happening because there was a magnetic field present around the conductor. So it was proven that electric conductors and wires can also cause certain magnetic field around them. Now this, how much magnetic field, how is the magnetic field, depends on the shape of the conductor that was present. So if you have a conductor which is straight, a straight conductor, the magnetic field will be in concentric circles around the conductor in a plane perpendicular to that of a conductor. So you should understand here that there is 3D. So if this pencil is my conductor, in this plane which is perpendicular to the conductor, there is magnetic field around it. So, and how is this magnetic field is determined by the right hand thumb rule. So that right hand thumb rule states that the thumb gives, you should understand that this is my right hand, and you should always use your right hand for this. So the direction of right hand, since it's a camera, you'll see opposite, but use your right hand to understand this better. So the direction of current is given by the direction of the thumb, and the curled fingers give you the direction of current. So when the conductor is upwards, like the current is flowing up, as we can see here, if the current is going in this direction, the magnetic field will be in this anti-clockwise direction that you see, right? And if the current in the conductor is going downwards, where again I switch my hand, okay, the direction of magnetic field will be in the clockwise direction, which is, as you can see here. So this is how the right hand thumb rule shows you the direction of magnetic field for different conductor. Up, anti-clockwise, down, clockwise. You can remember that, or very easy is to use your hand in the exam. That is the best one. Just ensure that you use your right hand for right hand thumb rule. Coming to magnetic field in a circular loop. So now if I take the conductor, make it a circular loop, how will the magnetic field be? So in that circular loop like this magnetic field will be going through it and form circles in a like this. There are two circles like this, as you can see. So they are both perpendicular to each other. They are in different planes. Okay, but they are forming closed loops in the circle. So the magnetic field lines are straight in the center. In the center they are straight. At the ends they form circular loops in a plane perpendicular to the circular loop at the end. And if you increase the number of circular loops, the magnetic field will start increasing. That is what is magnetic field through a circular loop. Using this logic, people made something called as solenoid. It's a metallic wire which is wound like this to form circular loops. Okay, and it is wound on a soft iron core, which causes it to be a solenoid. And when it is connected to a circuit, the magnetic field that it generates is very similar to what it looks like of a bar magnet. right? So the same magnetic fields you could have seen in a bar magnet. So this is solenoid is generally used to magnetize iron core. So what they do is they place an iron core inside the solenoid. It starts magnetizing the iron, which is called an electromagnet, because you have made this magnet using electricity. So these solenoids are generally used to create electromagnets, force due to electromagnetic field. So the force due to electromagnetic field is nothing but I place an electric conductor. We have already established that there is magnetic field around it. Now I bring another magnet which has much more magnetic field than the magnetic field caused by this conductor, such that this magnetic field is almost null and void. So I have current going. I have a big magnetic field, external magnetic field presence. So in the presence of these two, there is force that is created. So when there is force, what happens? There is movement. Whenever there is force only, there is movement. So when these two are placed such that they are perpendicular to each other, the object that is hanging will start moving, and the direction in which it will move is given by the left hand Fleming rule. So when there are two forces acting, one is the magnetic field force and one is the current, it causes motion in the object when they are perpendicular to each other, right? Because when they are perpendicular is when there is maximum force basically, and there is zero force when they are parallel to each other. You will learn more about this in your 12th class. So in the Fleming's left hand rule, what we understand is, so if this is my current carrying conductor, let's say it's carrying current in this direction, and this is my magnetic field, okay, then the force that comes is given by, you have to take your left hand here. So I have placed it, let me place it such that this is similar, okay. So the current is going in the upward direction, the magnetic field is in this direction. So you can see here my thumb was pointing out. So the force or the direction in which the object will move is outwards. You can see my hand on that side of the paper. It's easier. There is lateral inversion here. So that force is coming outward, which is pointing at you. That is the force of the motion that will occur. Now if I switch the magnetic field, right, I switch the magnetic field to the opposite side, I change my hand, the left hand Fleming rule will change, where the current is given by the pointing finger, the middle finger shows the direction of magnetic field, the thumb shows the direction of motion. So in that case, if I switch my hand, like you can see, the force of motion will be going towards the paper or into the paper. So it's going inside. That is how you use your left hand Fleming rule. Okay, so there are only two situations maximum here. You will be given situations where the current is going north to south and magnetic field is going east to west. Based on that, they'll ask you whether it's going out of the paper or into the paper. So you use your left hand very clearly, just the left hand, and you determine where the current and where the force would be, right? This is how you use the Fleming's left hand rule. Now coming to the domestic circuit that we have. In India, what happens is there is a big main supply, right? And from there, the current is distributed across to each and every house. So mainly there are three wires in this distribution: the earth wire, live wire, and neutral wire. Live wire is the positive terminal that carries the current. Neutral wire is the negative terminal which has zero. So that is how you create a potential difference of 220 volts in India. And there is an additional wire called the earth wire, which is there to prevent any damage. So this earthing wire is generally connected to a big metal plate below the ground. What happens is, let's say there's an appliance which has a metallic body, so it can accumulate charges, right? So all these charges are collected by that earth wire and it goes into the ground, because if you touch that, you will get the charge onto yourself. So it is a safety measure, okay, and it keeps any leakage of current to the metallic body of the appliance and its potential of the earth, and it is kept at a potential to get it onto the earth, so that the user will not get any severe shock. It's a safety measure. Coming to electric fuse. Okay, so electric fuse that you see outside is an important component of this domestic circuit. What happens is it prevents the circuit or appliance from any damage by stopping the flow of highly unduly sudden electric current. If suddenly there's an electric current, it stops that. So what it does is, like we saw the Joule heating effect, it flows and a defined measurement. So let's say you need a current of, maximum current that can flow in the circuit is 5 ampere. The moment the current goes beyond 5 ampere, this fuse will melt and it will stop the circuit from getting further damaged. Okay, and this overloading, what I just said, the change in current can also happen because of hike in supply of voltage. Ohm's law, increase in voltage, increase in current. So that process is called overloading. And when, or the live and the neutral wire sometimes come in contact like this, which can cause huge heating effect or issues. So in that situation, the fuse will protect it. This fuse, when it breaks, right, there'll be sparks in the circuit like this. Or even if you connect multiple appliances to a single socket, is also when there is lot of overloading in the circuit. So this increase in current in the circuit abruptly is also called short circuiting. So this completes your entire physics chapter. You might not feel like we have done much because we were it's a very there are two big chapters where there are a lot of numericals involved. We'll be doing a video with all the important numericals that you need to practice for board exams, where you will complete your entire physics revision. So until then, revise these chapters. You can always comment below for the WhatsApp link where we share the PDF of all these chapter notes, and there will be sample papers and practice questions inside it. Similarly, you can do that for biology as well. And you can please subscribe to the channel so that you can get to know when new videos come. Like and comment on this video if you really like this combined view, and if you would like for me to make other videos on different topics of CBSE class 10 physics and bio, please let me know. I will make videos on that. So until then, please study well for your exams. All the best, and do well.